Hey, welcome back. We are going to do the 2016 AP Calculus AB Practice Exam, free response question number 4. Two things before we get started, all right? Number one, follow me. That helps you, and it sends you notifications of when I put up any future videos, like free response question 5 for this exam, and free response question 6, or any other exam I do in the future, okay? Number two, like the video because that helps me. And while you're down there, pressing and clicking on that bell, if there's an exam that you want to see me do, throw that in the comments, and I'll try and get that done up for you. So hang on tight. I hope you've brushed up on your trigonometry because we are going to start free response question 4 right now. Number 4 reads, let S be the shaded region in the first quadrant bounded above by the horizontal line y equals 3, below by the graph of y equals 3 sine of x, and on the left by the vertical line x equals k, where k is in between 0 and pi over 2, as shown in the figure above. Find the area of S when k is pi over 3. All right, let's begin by figuring things out here, all right? Y equals 3 is this line right here, okay? Y equals 3. Y equals 3 sine of x is this curvy thing right here. Boop, all right? That's y equals 3 sine of x. All right, let's go here. We have the vertical line x equals k. That's that line right here where x equals k. And all right, that's my lower limit. And for all purposes, k is going to be pi over 3. But I need to know where the upper bound is going to be. And I say upper bound, how come? When I find the area under the curve, or the area between two curves, I need to integrate. So right now I know I need to integrate, all right? And I have my lower bound, which is k, which is, we're going to call pi over 3, all right? But what's that upper bound? Well, we don't have the calculator, so I can't set these equal. I can't put them in y1 and y2 and see their point of intersection. But, I mean, I don't know, this probably is going to come in at some place. If I need to solve for this x value right here, okay, I just set these two equations equal, and I can solve them algebraically. So sine 3 sine of x equals 3. Divide both sides by 3, and you know what? There is only one place I can think of where sine equals 1 within from 0 to 360 degrees, and that's at 90 degrees. And guess what we call 90 in radians? Pi over 2. All right? So this is going to be pi over 2. That's my upper bound. All right? So now I know how to do the area under the curve, but the area between the curves. I need to take my bigger function and subtract my smaller function. Okay, so which is which? The bigger function is the one that's further from the y-axis. In this case, it's the red line, or y equals 3. Minus, okay? The smaller function is the one that's closer to the y-axis, or the blue one. In this case, it's 3 sine of x. Don't forget we need dx anytime we integrate. They can take points off. I am going to factor out a 3. I like to work with smaller numbers when I'm doing calculus, if I can. All right? So if I factor out a 3 from here, I'm going to put that on the outside. So from pi over 3 to pi over 2, I have 1 minus sine of x dx. This is what I'm integrating. Beautiful, beautiful, beautiful. All right, let's continue this way down here. All right? Bam. Here, go here, go here, and let's color this up a little bit of orange. All right. If I integrate 1, that just gives me x. Okay. What do I take the derivative of that would give me a negative sign? Cosine. So when I integrate negative sign, I get a positive cosine of x. I want that from pi over 3 to pi over 2. And oh my God, please don't forget, I still got to multiply by that 3 that's out front. Do not forget that. All right, let's do some math, shall we? Let's put our upper bound in. We have pi over 2, and for this x, plus cosine of pi over 2. That's my upper limit minus the lower limit. Now I'm going to put pi over 3 in for these x's. Okay? Pi over 3 plus cosine of pi over 3. All right. And don't forget, we still got to multiply this whole thing times 3. Okay, can't forget about this on the outside. All right, a lot of people like to use the unit circle, which might be quicker, but I've always trained my brain to look at the sine and cosine curve anytime it's an increment of 90, okay, or my special triangles, my 30, 60, 90 triangle and my 45, 45, 90 triangle, when I have an angle that's 30 or 60 or 45. So you should know right off the bat, this is 90 degrees, pi over 2, and this is 60 degrees, all right? So the cosine of 90, here's 90, 180, 270, 360. Okay, cosine, that's 0. Cosine starts up high, it's the cup. Here, down here, down here, down here. Down. So it does this thing. The cosine of 90 degrees, or pi over 2, is 0. So this is going to be 0 plus pi over 2, which is just pi over 2. We still have our 3 on the outside that we're multiplying this by. Okay, minus, all right, pi over 3 plus 60. The cosine is 60. This is where it helps to know your special triangles. And again, some of you guys might know the unit circle, and that's fine. I just do it this way. My sides are 1, radical 3, and 2. The cosine of this angle is adjacent over hypotenuse. So it's 1 over 2. So cosine is adjacent over hypotenuse, which in this case is 1/2. All right, let's start simplifying this a little bit. All right, we'll distribute the negative sign. So we got pi over 2 minus pi over 3 minus 1/2. I just distributed this minus sign. Okay, I still got to multiply it all times 3. Let's distribute the 3. I've got 3 pi over 2 minus, 3 pi over 3, these things are going to cancel, minus 3/2. Okay? All right, well, it would be nice because this has a 2 in the bottom, and so does this. So let's multiply the middle fraction by 2 over 2. So we end up with, okay, we have 3 pi over 2 minus 2 pi over 2 minus 3 over 2. Now, I can combine all these. 3 pi minus 2 pi gives me 1 pi, and then I have minus 3. That wasn't bad because we knew our trigonometry, okay? That always creeps its head up at some point in the test where you got to know the cosine, sine of 30 or 60 or 270 or 45, okay? So know those basic ones, all right? 4b, the area of S is a function of K. Find the rate of change of the area of S with respect to K when K is pi over 6. All right. All right. There's a few things that jump out at me. The area of S is a function of K. So I'm just going to write that S of K. Okay? So let's just start with that. Okay? S of K. Find the rate of change. Rate of change is slope, which we like to call derivative. Okay? So we're going to find the derivative of the area of S with respect to K, which means I'm going to have a K in there, and then I want to find it when K is pi over 6. All right, we got what we need. So S of K equals, okay, well, the area of S, okay, the area of S, we just said that's the area, okay, of 3 minus 3 sine of x dx. Okay, we just did this. Okay, we just did this where K is pi over 6. So okay, whenever we're finding derivatives, we find the derivative first. Okay, we find the derivative first, then we find it at this time. So right now, we had said earlier, this intersects at pi over 2. And K was less than that. So what do we got? From K to pi over 2. We're not going to throw in pi over 6 for K yet. Okay? Right now, all we did is establish this function. That's the area under the curve from K to pi over 2. Now, the second part is, okay, as we move forward, they want us to find the derivative of this. So we're going to find the derivative. This is where things get, I mean, I want to say a little bit easier to find the derivative of this side, which means I also find the derivative of this side. Okay? So S prime of K is going to equal, oh, this is nice. This is nice because derivatives and integrals cancel. However, I want my unknown in the top, and I want my constant in the bottom. So before I actually do the derivative, I'm going to switch my bounds. Put the K up here and the pi over 2 down here of 3 minus 3 sine of x dx. But when I flip the bounds, I need to negate the value, okay? Now, I can take the derivative of this. This cancels with the integral, which takes away the dummy variable, and what value is here, variable is here, gets substituted in for this variable here. Okay, so let's rewrite this. We now have, okay, S prime of K equals 3 minus 3 sine of K. This is the derivative, and at that point, we want this when K is pi over 6. Okay, when K is pi over 6. All right, well, S prime of pi over 6 is 3 minus 3 sine of pi over 6. Pi over 6, okay, in case you didn't know, when we did part A, the reason we figured out, well, because number one, you're smart, that this was 90, okay, highlight would be easier to see, that this was 90 and this was 30 is because whatever pi is, we substitute 180 in for pi. 180 divided by 2 was my 90. 180 divided by 3 was my 60. 180 divided by 6 is 30, okay? So this is like saying 30 degrees. Again, we need our special triangle. Okay, let's do that to the top here. Okay, 60, 30, it's 1 radical 3 and 2. All right, now we want the sine of 30, which is opposite over hypotenuse. Sine is opposite over hypotenuse, so it is 1/2 the sine of 30. Okay, the sine of 30 is 1/2. So I have 3 minus 3 times 1/2. All right. And let's not forget something that I don't see that's not written on here yet. We forgot to carry this minus sign. So I'm going to negate this whole thing, okay, which means this makes it -3 and positive 3. So -3, positive. -3, positive, okay? Forgot to carry that negative sign. Remember that first problem, 4a? I was like, don't forget the 3. Okay, well, sometimes it's real easy to lose that you can do such beautiful work and forget to carry something over. All right, so I've got -3 plus 3/2. And if I combine those, I get -3/2. There you go. That's the answer. Okay, that's the rate of change of the area of S with respect to K when K is pi over 6. 4C, and this is the last one. Free response question 4 only has 3 parts, A, B, and C. This is C. Let's finish up. Region S is revolved about the horizontal line y = 5 to form a solid. Sweet. Write, but do not evaluate an expression involving one or more integrals that gives the volume of the solid when K is pi over 4. That is even sweeter. We only have to set it up and not do any of the work. So the brunt, okay, the bulk of this problem is going to be the explanation on the integral that I set up. Because in order to find an area under the curve or a volume of something being rotated, we always need an integral. All right? So let's start by writing the obvious. K is pi over 4. So at the bottom here, K equals pi over 4. All right? We still know this intersects at pi over 2. Man, that has come back every one of these problems, that bit of information we got from the part A. All right? But now I need to rotate this, okay? So I'm going to extend this, okay? And let's say if we got 1, 2, 3, 4, 5, 6, 7, 8, whatever. So 5 is right here, okay? 5 is right here. 5 is the horizontal line that I'm going to be rotating this. I'll do this in gray. Y = 5. And I'm going to be rotating this. All right? 1 and 4. Oh, my God. All right. So we'll do this in green. If I rotate this, it's going up like this, okay? And if I rotate the next one in blue, it's going to go up like this. Now, the numbers might not be exact on top, okay? And I'm going to have something that looks like this. 3 on 2, this line comes here. That's a reflection of y = 3. That's going to be at y = 7, which really isn't that important. And then we're going to have this blue one down here. If I reflect that across y = 5, I mean, it's going to look something like this. Okay? So I have this washer. Okay? I really have 2 circles here. I have an inner circle. Okay? This blue circle is right here. Okay? The whole thing. I want to find that out. Okay, but then I want to subtract the inner circle. Okay, so I'm going to find this whole big yellow circle, and I'm going to subtract this inner circle. And that should give me, because I have an obsession with these highlighters, this part right here. That's the yellow minus. Okay, so I'm going to try and find this. by taking the yellow and subtracting the blue. Okay, there you go. Now I got all my fancy colors. All right, in order to find volume, I need to integrate the area. All right, I need to integrate the area. So here we go. And it is always, if we're integrating, it's the bigger minus the smaller. Okay? These are circles. The area of a circle is pi r squared. All right? Pi is a constant, so I'm just going to throw any constant on the outside of my integral. All right? So my lower bound is pi over 4, and my upper bound is pi over 2. Now, this should be the bigger radius squared minus the smaller radius squared. A lot of your books might call the bigger radius capital R and the smaller radius a lowercase r. So the million-dollar question is, how do we come up with a radius? Well, the bigger radius is obviously the radius of the yellow circle. That's a bigger circle compared to the blue. Okay, so I want to find the radius of the yellow circle, then subtract the radius of that blue or green circle. So, starting from 5, I need to subtract the blue line from 5. The blue line, let's not forget, that was 3 sine of x. So I'm going to take my y equals 5 and take away 3 sine of x. That's the big R. 5 minus 3 sine of x. Don't forget, I need to square that. Take away the smaller radius. All right. Well, let's move this aside for right now. No, this one right here. The smaller radius is starting from 5 and going to the green line, which, let us not forget, the green line is just 3. Okay? So I take my 5, where I started, and subtract 3. That's the smaller radius. Don't forget, I need to square that. And for the love of the Lord and everything holy, if you do not use dx, they can take points off. Okay? So I've got this big whole thing right here. Now, that was the explanation for everything. If I want to clean this up, I can. But my answer is going to be as follows. Let's highlight this. The integration from pi over 4 to pi over 2 of this stuff right here is my answer. Now, the only thing I can clean up if I wanted to would be that second radius, this part right here. 5 minus 3 is 2. 2 squared is 4. So I could write it, if I wanted to, pi on the outside, okay, from pi 4 to pi 2 of 5 minus 3 sine of x squared minus 4 dx. That's a cleaned up version of it, okay? We don't even have to solve it. All we had to do is set it up. The explanation for the setup was a lot more work than the setup itself. Okay? So we are done. That's weird because most problems like this have a part D where we would now have to evaluate that integral from part C. But lucky for us, this is the year 2016, and they didn't have that. We're done with free response question 4. Like the video, that helps me. Follow me, that helps you. And I will see you for free response question 5. See ya.